Oh, thank you, Edmund. Thank you, everyone, for your time. Let me share my screen and start the presentation. Okay. Edmund, can you see my screen?
I can see it.
Oh, thank you, Heinrich. Okay, so let's go with HPC kit and with HPC tools for one API and Intel products. So today was a number of talks about performance analysis and roadmap. So let's go for cluster systems and for distributed HPC. And so to start, let's remind you that one MPI initiative has two parts. The first part, it is the initiative and open specification. And second part, it is a set of software products targeted for efficient usage of of hardware accelerators and CPUs. And as described before, we have plenty of tools, and all tools combined to for toolkits related to application domains. So right now, our talk will be dedicated to Intel One API tools for HPC. Okay, let's switch to our tools, and here you can see that we have base toolkit. It is a light blue, and we have additional to base toolkit. We have HPC toolkit and tools in dark blue. So we have compilers. It is classical compilers. So usual Intel compilers that probably all of you are aware. These 2 days we were focused on new gen of compilers, but in HPC toolkit for compatibility, backward compatibility, and to support legacy products. We have also classic compilers, C, C++ compiler, and Fortran compiler. For libraries, we have Intel MPI library, and it is a key ingredient of HPC toolkit. And most of time for this talk will be dedicated to Intel MPI library and usage and how to use it with Intel GPUs. The only note that Intel MPI library usually is using in clusters, and so some of you who has NDA with Intel can use it on Dev Cloud with ATS cards and with PVC cards, but with publicly released cards, so so it is hard to use Intel MPI library. So that's why I have no demo. So I have only slides. But those of you who has NDA with Intel, they can test it on not released hardware. So we encourage you to sign NDA with Intel. So usually it is not too hard. It is about 15 minutes from Intel side, and you need to sign documents electronically and send back to Intel. So, and after this, you will be able to use NDA part of Dev Cloud with Intel MPI, with data center, graphic accelerators, and so on. So once again, we encourage you to sign NDA and to try to test data center accelerators. Also, for HPC toolkit, as you can see, we have Intel Inspector, and right after my talk, Heinrich will present some insights on this. And also, we have Intel Trace Analyzer and Collector and Intel Cluster Checker. So I have no slides for Trace Analyzer and Collector and Intel Cluster Checker. so only mentioning of it, but we can, if you want, so we can have special session about trace analyzer and collector and Intel cluster checker. So please feel free to ask our committee and Edmund to arrange special hands-on and practical sessions for MPI and MPI performance and correctness checking if you need, of course. So this is not GPU specifics, so it is usual, and we provided in the past some sessions about MPI library, classical usage, about trace analyzer and collector, and of course for cluster checker. So today our plans is to focus on hybrid usage in cluster of CPU and GPU. And of course, you can download one API HPC kit by the link. So so you can see it here. So, and the slides are already available. So probably every one of you has an access to PDF with this. So you can download it by the link. Okay, so this is a classical slide for Intel MPI. So Intel MPI, it is the intermediate software. It is the library that makes able for high performance distributed applications and different domains, usage of HPC clusters with different interconnect, and the Intel MPI library is highly optimized. And we have optimization, specific optimizations for interconnect and specific optimization for Intel architecture. And also, so Intel MPI library can be tuned for specific application, and the Intel MPI library has integrated fast tune utility. So on launch so we are tuning Intel MPI library in Intel on Intel clusters available for development team, but of course, usually we are not using your cluster in your data center, but you can tune Intel MPI library on your specific cluster with MPI tune utility. It is included to package distribution package of Intel MPI library, and use settings from MPI tuning on all next launches of Intel MPI library to achieve better performance on your specific cluster. Also, Intel MPI library can do it for you for every launch, so it can spend some milliseconds on startup to find the optimal parameters and then use it during the. So we have auto-tune functionality in Intel MPI library. And of course, we are supporting almost all Intel hardware. So all Intel Xeon, Xeon processors publicly released. And we're supporting Intel interconnects, and we are supporting Mellanox interconnects for clusters. So this is a general slide. So we have it on all sessions dedicated to MPI. But what's new in version 2021? So some of you asking about availability of 2022 because we have one API release 2022. So why we have only Intel MPI 2021? But yes, we have different versioning between components of one API packages and whole package of one API. And this is a versioning of Intel MPI library related to functionality of Intel MPI library. So, of course, we have plans for major releases, but right now we have 2021 version, and the key new features in 2021 in comparison with 2018 that now we are focused on HPC in cloud. So we have strong integration with Google Cloud Platform, with Amazon Web Services, and we are so of course Intel MPI library is working in Microsoft Azure and other clouds. So you can use. So we have some success stories you can find in Microsoft Azure, in Oracle Cloud, and other HPC clouds. And we are working on optimizations for these clouds very hard, I guess. But in release notes, we announced tight integration with Google Cloud Platform and Amazon Web Services. But keep tuned. In next release, we have great news. So when Intel MPI library will be available, those of you who has downloaded it and provide email for download, so you will be notified about new versions. And our TC team will prepare these notes with great news about Intel MPI library. So for hardware support, of course, we are supporting Intel Xeon Scalable third generation with codename Ice Lake. We're supporting Intel Ethernet cards, Mellanox InfiniBand cards, and we are supporting Intel GPUs. So it is mainly for data center accelerators. So as soon as this will be publicly available, so every of you can use it with Intel MPI. And we are focused on scalability, improved startup time, so stability and performance for interconnect providers, and we have spawn improvements. So we have some reports about spawn issues on Windows, so it's finally fixed with workaround, and we plan to pull this workaround as complete solution. And new technologies, so Intel is strong and main contributor to DAO's file system, and Intel MPI is supporting DAOs, and we have so Intel MPI previous versions announced support of Docker containers and Singularity containers, and now it has extended containers, extended Singularity support for different job management systems. Okay, so GPU. So so I guess most of you knows Intel MPI. So for GPU, so MPI primitives can be used for communications between GPU. So we have three levels of GPU support in MPI. So it can be host-centric MPI support with GPU awareness. It is the current status of Intel MPI. When host initiating communications, but host knows where is the MPI buffer located. So host initiating communication, and it can use GPU memory, and it knows where is buffers located in host memory or in GPU memory. And the next level is GPU-centric MPI, when GPU kernels can initiate communication. So it is in progress for Intel MPI. So stay in touch, and we will announce about it. So with recent version of Intel MPI, it was announced that multiple GPUs with multiple tiles can be used for Intel MPI. Of course, you can use manual decomposition, but Intel MPI has some default settings, and Intel MPI provides to you ability to assign different MPI ranks to different GPU tiles and slices. And also Intel MPI can allow users not just to offload computations, but also use GPU memory pointers for Intel MPI. So we will see it in separate slides. Okay, so first section is how to pin your GPU parts to Intel MPI ranks. So we have several environment variables. So by default, so we have IMPI offload family of environment variables. So some can select a topology library, but for now the only one choice is level 0. Also, granularity of selection, it can be tile. By default, it is tile, domain size. So how many tiles can be used by Intel MPI library, and which particular devices should be assigned to Intel MPI infrastructure. So it is by default automatic GPU resource distribution, so no code changes, and it is NUMA aware. So it will try not to use remote devices on different NUMA node for Intel MPI ranks. So, but example, so default it is 4 ranks. So example is taken from last year supercomputing talk. So probably some of you is familiar with this, but anyway. So by default, if we have 2 ranks on NUMA node 0 and 2 ranks on NUMA node 1, so and each NUMA node has GPU. So of course we have placement of nearest GPU tile to nearest rank. And Intel MPI will not place GPU parts on remote NUMA node and assign it to local ranks. And you can check GPU distribution by IMPI debug environment. So general information with level 3 and more detailed information with level 120. So it is default, but of course you can override default with environment variables. So by default, for example, you can change domain size from outer -1 to needed for your application. So for example, you can specify domain size with 2 and then assign and then assign so for rank different different number of GPU parts. So if you have not uniform distribution of your work, so you can assign non-uniform compute resources on different NUMA nodes. Okay, and for example, you can change from tile to device, and in this case, you can for GPU, as you have different tiles, so you can assign for each tile for two parts for each rank on NUMA node. So it is a granularity of assignment. And changes the float domain size for this. If you have on NUMA node 1 only 1 rank, so you will use only half of GPU 1, so with domain size. And if you want to use only specific GPU, so you can specify GPU number for Intel MPI library and use only specific GPU. In this example, we are using GPU 0 and we are not using GPU 1 for some reasons. Probably we are using GPU 1 for something else, or just we have no work for GPU 1 or by any other reasons. And of course, you can specify bit mask for use specific ranks with specific GPUs. So you can mix with bit masks assigned parts of GPUs who will be for different ranks. Okay, so this is about pinning of GPU to MPI ranks and about how to use buffers with Intel MPI. So we have different usage with Intel MPI offload, so it can be disabled, it can be auto. So if you runtime loading level 0 automatically, or Intel MPI can do it for you. And the execution model. So this is example how to use Intel MPI with OpenMP offload. So initially we are calling it naive method. So with OpenMP offload, you can place data, assign data to ranks, and place some values to GPU, then perform some computations on GPU, and then return back and communicate with MPI send. So send buffers return back from offload to different ranks. So it is a offloading method, and this is a method for communication between hosts. But MPI knows where values are located. And second method is OpenMP. It is using pointers. So as described before, Alina today described how to use device pointers in OpenMP offload. So in Fortran application, but the same can be used in C, C++ applications. So it can be also used with Intel MPI. And as you can see, so pointer provided to MPI send, and it is not copied back from GPU. So data located on GPU, and runtime MPI runtime doesn't copy it from GPU. So MPI runtime provides to communication infrastructure, provides pointer to data on GPU and transfer it transparently for MPI infrastructure. Usually it is better than copy from and back to card. And of course, we need to compile application with OpenMP target. So if we are using Intel GPUs, so we can use it the same way, the specified way for C language and for Fortran language, and execute it with IMPI offload equal to let MPI infrastructure to load offload library. Okay, so this is about MPI and GPU. So any questions so far? Okay, so next section is how to check performance of MPI application. And today we had a talk about Intel vTune profiler. And as part of Intel vTune profiler, we have application performance snapshot. It is targeted for, in vTune, you can see timeline with details about performance and resource utilization, but application performance snapshot is usually targeted to have statistics about your application. So it is a general information about overall performance of your application. So this is an example of HTML report for application performance snapshot, and you can for MPI application you can have at the end of application you can have summary information about execution time of your application, about some general overviews of microarchitecture usage, about memory stalls, vectorization, I/O. And for distributed applications, you can have information about MPI type and usually it is more important to have information not only about MPI time but about MPI imbalance. So comparing overall time and the MPI time, so usually we can treat MPI time like overheat. So in ideal situation, MPI time should be equal to 0. So in this case, we have infinite bandwidth and 0 latency and ideal hardware. Unfortunately, right now we have no such hardware and software stack. So in this case, MPI time is not 0, but worst situation is that sometimes due to not ideal synchronization between MPI ranks and between OpenMP regions, we have some imbalance. Imbalance means that MPI runtime spend time to waiting counterparts. So for example, if we are receiving something, but our peer is not sent to us needed data, so we are just waiting for our peer, and we are spending time without computations, we're just spending time in MPI progress. And application performance snapshot can calculate time in MPI progress and demonstrate time spent non-efficiently in terms of application synchronizations. Of course, MPI application performance snapshot can demonstrate you top 5 MPI functions in terms of elapsed time. So it is targeted to large scale runs, because before application performance snapshot, we have the MPI performance snapshot, and we have Intel trace collector and analyzer, and some information about MPI time. Of course, you can get from iTech summary page. But for application performance snapshot, it is a lightweight utility, and it's proven for collection on data collection on 96 kilorangs and whole spectrum with MPI whole spectrum of metrics with MPI imbalance on 46 kranks on real-time application, tested with real-time applications. And of course, trace sizes is much smaller and lower overheat, and it is not placed here, but you can control collection of application performance different regions of your application. You can specify with MPIP control and with API within your application to specify what needs to be collected by application performance snapshot, and you can have some regions in your application, specification for regions in your application, and application performance snapshot can collect at single launch, it can collect data from different agents, even overlapped agents in your application. So it is a very handy functionality for application performance snapshot, and usually in Intel for all HPC applications we are using in hardware deals, we have enrichment in applications with APS instrumentation calls and collecting data of performance of different regions of application. So it is a part of vTune profiler. So for multi-node launch, APS provides aggregated metrics. Of course, with you can select particular rank. It plays data, binary data for each rank, and you can specify which rank needs to be analyzed with application performance snapshot. Collection is pretty simple. Just use APS before your application with MPI run, and collection can be adjustable to decrease overheat and to decrease size of traces. By default, overheat is about 1 or 2%. And in other modes, when you are collecting imbalance, by default it is disabled. and we have two different methods to get imbalances. For example, so if you are using Intel MPI, so it is a lightweight to get imbalance because application performance snapshot can get it from MPI runtime data about imbalance. But if you are using different MPIs, and the application performance snapshot can be used also not only with Intel MPI, but in worst case. So there's always bad situation when you are using not Intel MPI. Application performance snapshot can instrument MPI code with barriers. So it can insert barriers in collective calls and in MPI calls, finalizing MPI communications and collect data spent in non-efficient communications. It is much more overhead with inserted barriers, so it is recommended to use Intel MPI and APS to have imbalanced data more lightweight. So by default, at the end summary report. So it is some application, MPI bound application, and we have some insights, just like in VTune, insights that that for MPI bound application, if you want to 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 optimize it, so you need to use specific tools like Intel Trace Analyzer and Collector, or like MPI profiling tools, because this is just summary. But our engineers, some of our engineers prefer to use APS even instead of Trace Analyzer and Collector, just enriching source code with ITT API and with MPI control calls to get insights about performance of particular communication patterns and particular parts of application or particular computation kernels. And of course, it is a summary, and you can get a detailed report in command line about OpenMP imbalance, about CPU utilization. So my preferable, it is the MPI message sizes, because MPI runtime with MPI adjust, you can tune your MPI infrastructure for particular message sizes to memory bound and not topology and GPU time. Let's go to, so detailed report can be used in command line, and as you see on some chart, GPU also can be collected. So GPU and PCI Express information also collected with application performance snapshot. And here is insight on new graphic functionality for rank-to-rank communication metrics. So if we have a lot of ranks, so if we have 4 ranks, so provide metrics with communications is pretty good. It's pretty simple. Just put it metrics. In iTech, you can see colored table with data. But when we have several thousands of ranks, so usually you need something better than just colored table. So we have graphic representation and some utilization of natural intelligence of human brain to understand communication patterns between ranks. And for GPU metrics, so for GPU metrics, it is a execution efficiency. So time spent in GPU in comparison with elapsed time. So GPU utilization when GPU is busy, how many execution units is utilized when GPU is used, and GPU occupancy, and state of execution units. So percentage of active, idle, and stalled, and the float activity. So if you are using Intel GPUs for data center, so with the application performance snapshot, you can get you can easily get information about efficiency of GPU usage on your system on your particular launch of your application. And new functionality, it is outliers. So application performance. So when we have imbalance, so it is imbalance for your synchronization. And imbalance, it is very important metric. And when you have only few ranks, so by checking MPI functions on each rank, you can find out what is the root cause of your imbalance manually. But when you have plenty of ranks, so sometimes it is it is hard to understand root cause of imbalance. And Intel and the application performance snapshot introduces in recent versions introduces outlier detection. So it is based on statistical tests. So it can check outliers and provide some information about which ranks have behavior statistically not as other ranks. So it can demonstrate to you that we have some ranks with not usual behavior and informate you that you need to pay attention on particular those ranks to get information about outliers. So you need to get APS reports and filter metrics for MPI imbalance. And after this, so you need to go to. It is not shown on summary page, but you can get the information from MPI Insights and from Labs time. So let me check with my Google Chrome. So for example, I have small run yesterday and collected APS report with MPI imbalance. So for MPI time, you can have information about outliers. So I have, this is as you can see, MPI IMB, MPI ping pong. So those of you who remember what is ping pong, so it utilizes only 0 and rank 0 and rank 1. So we have 4 ranks in this launch. So for outliers, of course, we have rank 0 and rank 1. So rank 2 and rank 3 stay in barrier, but most of work in rank 0 and rank 1. So as you can see, application performance snapshot clearly selected rank 0 and rank 1 like outlier. So usually it is not just a static picture of HTML report. Please feel free if you see red flag. So check red flag, and probably you will find something wonderful in application performance snapshot, like detection of statistical outliers. Please use this functionality, and probably it will save a lot of your time if you have bad nodes, if you have not balanced workloads in your MPI application and so on. Because usually when you see top MPI functions, we have 5% for MPI receive. And only if we know about application behavior, so we can realize that we have not balanced work distribution. But with the outliers, of course, we can clearly see that we have outliers with rank 0 and rank 1. So please, if you have something in red, so check it with your mouse pointers, and the application performance snapshot will show you some insights. So usually it saves a lot of your time and also recommends you what to do next. For example, to use vtune to collect memory access analysis or something like this. Okay, let's return to my slides. Oh, it is not. Okay. And so it is so once again, all of this is a part of one API HPC toolkits. And also in HPC toolkit, we have trace analyzer and collector, and we have cluster checker. And with HPC toolkit, we have also as you can see, we have also Intel MPI benchmarks related to GPU. So you can check performance of your MPI primitives and collectives on Intel GPU with our standard benchmarks. Of course, it is open sourced, and Intel MPI benchmarks GPU versions can be found on GitHub with Intel MPI benchmarks repository. So if you have GPU on your cluster, so you can check performance of MPI primitives with MPI with Intel MPI benchmarks. So I will try to launch it, but it will crash because particular GPU from my NUC is not supported. But you can see, so it's killed segmentation faults. But with GPU benchmarks, you can use usual benchmarks with usual collectives and point-to-point applications. So let's return to this, and that's all for my presentation. So looks like I finished early. So any questions?